Gonna go over the section 19300C, Fluid Statics and Dynamics. And this one has different knowledges or subsections. The first one is knowledge K104, which is water hammer. So we're gonna start with water hammer, but I just wanna, before I start, I like to mention that I'm gonna divide this into videos because in this section is where we start like having like longer sections, like with more information. So this section is gonna be a little bit larger than previous section that we have seen in the, in this thermodynamics subject, right? So I'm just gonna divide this video in two. I'm just gonna go over like the concepts that we're gonna see in this section. And then in another video, I'm gonna just go over, the problems and how to solve them. Okay, so water hammer. So water hammer is pressure surge that's gonna occur, when we're gonna have this sudden change in the flow of the water within a piping system. And it typically happens when a valve is quickly closed. So right now we have this valve that is initially closed, right? So there's water in here and there's nothing here. Once we start opening the valve, we're gonna start having some movement of the fluid. It can be water, it can be oil, it can be like whatever it is, right? We're gonna have some movement of this fluid, right? So then what happens if we quickly close the valve? Well, this gonna cause like this shock wave that is gonna travel. We're gonna cause a shock wave, right? And it's traveling across the pipe. And this can cause a significant damage to the pipe or a valve or other component in the system, right? So when water is flowing through a pipe, it has a momentum, right? It has some kinetic energy. So when the flow is just suddenly stopped, the energy is converted to pressure, right? So that's why we say we have this pressure surge. So the increase in pressure creates a shock wave, which can cause the pipe to vibrate and can even cause the pipe to burst, in extreme cases, right? So water hammer is going to be this pressure surge wave. When fluid in motion suddenly stop, it's also called hydraulic shock, and it can happen in a system with liquid and gas, right? When it happens in steam line, it's like condensation. That's how we call it. How can we prevent this? So we can prevent this in different ways, right? We can minimize water hammer by venting the system. We can also open or close the valve very slowly, right? So we can reduce this, momentum, this kinetic energy. Also, we can start a centrifugal pump discharge, either closed or throttle. Another important thing for gas lines is to drain or warm the steam lines. That's also going to be very, very important, right? Because we're going to have this difference in temperature, right? If we have difference in temperatures, it's also going to cause like this pressure spike. Also, if we reduce the flow prior stopping a large pump, that's gonna be also important in order to minimize the water hammer. But another way that we can do to actually prevent it is by installing devices such as air chambers, because they can provide this cushion of air to absorb a shock wave, or pressure relief valves, right? So we have in the GFIS, we're gonna talk a lot about pressure relief valves because we use them a lot in nuclear power plants. So that's what we're gonna talk to. We talk about pressure relief valves at all and safety valves. So those are like two main type of valves that we use a lot in power plants. So, but if we have this chamber, right, this air chamber in a system, this is gonna allow the pressure to be, released gradually. We're gonna have this cushion of air that is gonna absorb the shock wave. Or another way that we can actually prevent it is by properly design and install a piping system, to minimize, the risk of water hammer as well. So that's gonna be important. So If we have like elbows, like in a certain way or certain positions, like, different things, that's gonna be important. But the main things, like for the exam, like you have to take it, like it's gonna be this information right here. That's all you need to know. So then we jump to talk about pressure spikes. So there is a direct relationship between mass flow rate and pressure spike in a piping system, right? The mass flow rate, it refers to this amount of liquid, right? We're gonna have this amount of liquid or fluid that's gonna pass through a given point in the piping system per unit time. That's flow rate. So while pressure spike, it refers to a sudden and brief increase in the pressure. So brief increase in pressure, right? It can be, I don't know, at a certain point. So when the mass flow rate of fluid in a piping system increases if we increase the mass flow rate, that means that the velocity of the fluid also increases. So this increase in velocity results in a corresponding increase in kinetic energy, right? So we increase the kinetic energy, that's gonna translate into a pressure spike, right? So if the mass flow rate, suddenly decreases, the kinetic energy in the fluid is converted to pressure energy, which can cause a pressure spike in the system. So, and similarly, a sudden change in the mass flow rate, if we had a sudden change in the mass flow rate, such as a sudden start or stop of a pump, that can cause a pressure spike in the system due to this sudden change in the kinetic energy. So that's why it's important to design and operate this, a piping system with consideration for the mass flow rate. So it's going to have a direct correlation to the mass flow rate, right? So if we properly design and maintain a piping system, we can help to prevent, these pressure spikes and avoid any damage to the piping system and equipment. So that's why this is important. So, and here we also see, right, that the longer the pipe, the longer, or it's gonna take a longer time for the shock wave to dissipate than in a short pipe, right? So that's gonna be the difference between these two, and we're gonna see examples when we go over the GP questions. Another thing that we discuss or we see again, like if we see this like very often, is gonna be the volumetric flow rate, and volumetric flow rate is a measure of the volume of a fluid that's going to pass through a given point in a piping system per unit time, right? So, per unit time. So, volumetric flow rate is a critical parameter in fluid mechanics, and it's just to describe the rate at which a fluid moves through a pipe, a pump, or other component of fluid handling system. And it is important to accurately measure and control volumetric flow rate in order to ensure the proper operation and efficiency of the system. So for the volumetric flow rate, we have different formulas, but it's usually what we do for volumetric flow rate is calculated by multiplying the cross-sectional area, right? If we have a cross-sectional area, we multiply that it's going to be the cross-sectional area of the pipe by the average flow velocity in the fluid. So the cross-sectional area is going to be typically measured in square meters or square feet, while the flow velocity is measured in meters per second or feet per second. So by multiplying these values, the volumetric flow rate can be expressed in units of volume per time, right? And that's gonna be right difference. We're gonna see this relationship also between mass flow rate and volumetric flow rate. So this difference between this mass flow rate and volumetric flow rate is the unit measurement and also the physical properties of the fluid being measured, right? But there's a relationship. So mass flow rate is gonna refer to the amount of mass that passes through a given point in a piping system per unit time, right? Is the mass over time basically. And it's going to be expressed in units of mass per unit time, such as kilograms per second or pounds per hour. So mass flow rate takes into account the density of the fluid, right? as we can see in here, it takes into account the density of the fluid, which, it can vary depending on factors such as the temperature and pressure. So that's going to be important. So the volumetric flow rate, on the other hand, is going to refer to the volume of fluid that passes through a given point in a piping system per unit time. And that's going to be, as we mentioned, expressed in volume over volume per unit time, such as liters per second or cubic feet per minute. So, or GPM. So volumetric flow rate does not take into account the density of the fluid, but rather is based solely on the volume of the fluid that is flowing. So that's going to be one of the differences. But in here we have a relationship as well. So we have the relationship of a volumetric flow rate that is going to be proportional. It has a proportionality. It's proportional to the differential pressure. So this is a formula that we're going to use a lot, and we're going to go over examples. But then when we go over to mass flow rate and its relationship, remember, this is the formula for the mass flow rate. Mass flow rate equals the density times the volumetric flow rate. We can use the same relationship here to determine that the mass flow rate is equal to the density times the square root of the differential pressure as well. So, we can start making those getting into figuring out, okay, what are the formulas that I can use and how I can relate, the mass flow rate to the differential pressure. It's just trying to relate those things, right? Because we're going to have some questions that are going to take us there. So that's going to be very, very important. So then now we're going to have a steam generator. For people who does not know, steam generator is like a big heat exchanger, and it typically is, so it's gonna use is used to convert water into steam, right? Using heat from a fuel source. We use it in the nuclear industry, but they're also used for natural gas and coal industries as well. So the steam generators are commonly used in power generation facilities, to produce steam that is going to be used to power turbines and generate electricity, right? So that's the main purpose of steam generators. And maybe I already talked about that in another video, but it's important for the people it's their first time here to know that. So the basic operation of a steam generator is going to involve heating water to its boiling point and then transferring that heat from the fuel source to the water in order to generate steam, right? So the steam is then gonna be directed to a turbine, right? We're gonna transfer the steam that we generated in the steam generator, so that's why it's named, to a turbine through a piping system. That's why it's very important to know all this other stuff, right? That's why it's important to know about pressure spike, about water hammer, condensation in the steam line. That's why it's very important, because how am I going to transfer this to a turbine, right? I need to know that before I transfer my steam to a turbine and start generating electricity. That's important, so bit. This is the basic operation. Again, the basic operation of the steam generator involves this heating water, boiling it, then transferring heat from the fuel source to the water in order to generate steam. So the steam is going to be directed to this turbine. So, and then we're going to use it to produce this mechanical energy that is then converted into electrical energy. So mechanical energy and then into the grid to electrical energy. I mean, there are other steps that we will look into future videos, but for now, it's important to know this. So in order to remove the moisture from the steam generator, because this is going to be important, right? So here we have our primary inlet, we have our hot leg, and we're going to have our cold leg, right? This is going to be connected to the primary, right? That's going to be important. This is like the steam outlet, because this is going to the turbine. This is going to go to our secondary system. In a way, we are kind of like this is dividing the primary from the secondary system. So here, this is gonna be very, very hot, and this is gonna be very, not very cold, but there's gonna be a temperature difference right in here. But one of the things that we are trying to see in the examples from this section is that we maintain constant level at the steam generator. The steam generator, what comes in or what comes in comes out, right? This is what comes in here on the feed water. This is what comes out. So we have feed water entering the steam generator, but we also have the downcomer, and we will go over that. So we're gonna have two different places where water and steam are gonna come in, but we need to make sure that what comes in comes out, right? This is principle. So we know that that is true. So what happens here is that we have moisture removed from the steam generator that is gonna be returned to the downcomer, and that's not gonna affect our feed water system. So that's kind of like what we're trying to like say here, right? To declare, if you like it. So we're trying to declare that what comes in comes out. That's basically it. Trying to maintain constant level at the steam generator. That's something that you need to remember. There's going to be a question about it, and there's a question about it. As long as you know that, you are good. But okay, so let's go over that. So in order to remove moisture from the steam generator, the steam is typically passed through a series of separators or air drums. So these devices use centrifugal force or gravity to separate the moisture from the steam, allowing the dry steam to be directed to the turbine. So that's what happened in some systems. So then the separated moisture is then returned to the downcomer, which is a section in the steam generator that collects the water and directs it back to the feed water system, right? So in order to ensure that the moisture does not affect the feed water, it is typically passed through a moisture separator, right? Which is going to remove any moisture and is going to ensure that only dry steam is returned to the downcomer. So that's basically what it is, right? We just need to ensure that only dry steam is directed to the turbine, so the steam generator can operate more efficiently and generate more electricity while minimizing wear and tear of the equipment. So that's the purpose of it. That's basically it. So for now, we don't need to know more about this. So another thing that we need to remember is in this section, knowledge K106, we're gonna kind of like refresh on conversion from pressure units from PSIG to PSIA and vice versa. Also, we're gonna be asked a question about moisture, right? How to calculate moisture. So we're giving moisture, if we're giving the quality, we just need to calculate the moisture, and this is gonna be the formula, right? Like very simple stuff like that. Then in this section, another thing that we see, it's we're gonna talk about the steam generator shrink and swell. So usually I get conflicted information like on the internet about this. Just be careful. When we talk about shrink, we see an increase in the steam demand. We see an increase in temperature. We have less boiling on the secondary, and the level, the water level in the steam generator is gonna drop. So that's what we see usually. You just need to be careful because you will find the complete opposite on the internet about this. So then we have the swell, right? The swell is gonna be a decrease in the steam demand. We're gonna see the opposite, a pressure reduction. We're gonna have more boiling, meaning an expansion, right? That's what is said is swelling. And that's gonna create an increase in the water level as well. So we just need to make sure that we understand that part. Shrink, it's gonna decrease the level. So lowers the level. That's important. Swell, when we talk about swell, we are increasing the level. That's something important to remember. As long as we remember that, we remember like the basics of it. So then there's gonna be like, I think only one question probably about the reactor coolant system pressure spike. So a reactor coolant system pressure spike. So for instance, we have, the reactor, we have the primary piping. So what's gonna happen if we have like the pumps on the RCA pumps, no matter what happen if they stop, right? We're gonna have loss of force circulation, right? Meaning, if we have loss of force circulation, we are gonna increase the temperature in here because we are not circulating like this hot water here is gonna get hotter, right? And whereas the water on the other side, on the RCS, is gonna decrease because we are not exchanging any heat. So is on the heat side is gonna get hotter. What's on the cold side is gonna get colder, right? So that's what's gonna happen. So, and also another thing is to remember that in a solid system, we're gonna have this small temperature difference is gonna produce a large differential pressure. Just keep in mind, right? What's gonna happen if we have a solid system? So imagine like this is just filled with water. That means that that's a solid system, for instance, right? So that's something that we try to avoid because if we always need to prevent a loss of force circulation because even like nuclear reactors are designed with this redundant safety system. We have this backup cooling pumps, emergency coolant injection system. We have this passive cooling system, so we can rely on natural convection, or since we have other passive means to circulate coolant through the reactor. So we have all these systems that are designed to activate automatically in the event of a loss of force circulation or other emergency and help maintain coolant flow and prevent like overheating of the fuel rods in this case, right? Because if it gets hotter, we don't want to affect the fuel rod. But also reactor operators regularly monitor the coolant system for, changes in pressure, right? We need to monitor changes in pressure, changes in the flow rate, right? Because if the pump, we are constantly checking the flow rate, and also changes in temperature, like we talked about. So that's gonna be very important. So, and this also includes like adjusting the flow rate of the coolant through the reactor and, activating or the safety systems if necessary, to prevent a loss of force circulation. So that's why that's important, right? And that's why we talk about pressure spikes. So this is related to what we saw initially, right? So, I really like the progression of these subjects because, we can relate one thing to another. So now we are also gonna see the importance of venting a centrifugal pump, or what I call it a CP pump. So venting a CP is important because it ensures that we either like remove air from the pump and the suction piping and prevent all these air pockets from forming inside the pump, because all these air pockets can disrupt the flow of liquid through the pump and reduce the pump's efficiency, right? We are trying to be as efficient as we can in a power plant, so that's why it's important. So, and this also can cause cavitation and damage to the pump over time. So, and we're gonna get to the cavitation point, but this is taking us to that subject in a little bit. But there are a few ways to vent a centrifugal pump. So, one common method of venting is gonna be vent the valve or vent plug that is located at the highest pump in the pump and suction piping. And this allows air to escape as liquid enters the pump and fills the system. So another method is to use a priming pump or other device to force air out of the system and prime the pump. That's what this means when they say or just prime the pump, right? So let's say, so it says venting the pump prior to start. We need to vent it prior of starting the pump. Like we need to do it before. Like if we do it after, like we are just not venting anything. Making sure that all entrap air is removed. So air trap, water will be displaced and pump capacity will be lower. Low flow, low discharge head, right? So we don't want that to happen. So that's why, it's important for us to, vent the pump. Then we're going to take a look at also gas binding. So gas binding or vapor binding can also occur in a pump, right? So, which this can cause a reduction in the flow rate as well, same decrease the efficiency and potentially damaging the pump. So, and that's gonna generate an extra cost. We don't want to damage the pump, right? These pumps are expensive, especially the pumps from the RC. Like those are expensive. Like these pumps, I don't even want to know. I just don't want to know how expensive that's gonna be. So we're trying to always secure all the pumps because that's important. So for this, in a pump, gas vapor binding is gonna occur when either gas or vapor becomes trapped in the pump impeller or volute or the volute, and it's gonna prevent the liquid from flowing through the pump. Right? If we have air trapping here, we're not gonna have fluid coming in and out from the pump, right? So air is trapping there. That's gonna create an issue. So this gas or vapor binding in the pump can occur for similar reasons as in a piping system, which include like changes in temperature, pressure, changes in the composition of the fluid being pumped, or the design of the pump. But it is more likely to occur in pumps that have a low net positive suction head, right? So we're gonna talk about that. So there's gonna be an entire section of pumps, and we will go over that in more detail, right? But it's important, right? We're gonna have this low net positive suction head, and we're gonna go over to explain what that is. But uh, since we're gonna have this low value, that means that the pump may not be able to draw enough fluid to prevent cavitation and gas binding. So if we don't have enough fluid, we're gonna create more gas binding in there. Also, it is important that we select, a good pump for the application that we are looking for, and we need to make sure that we have sufficient net positive suction head value. But it's also important to install like, I don't know, it can be like a suction strainer or another device to prevent this gas or vapor from entering the pump. And it's important, obviously, regular maintenance and inspection of the pump can also prevent this. Also, identify potential issues and taking corrective action as needed as well. That's very, very important. And that's something that, distinguish the nuclear industry in general, because we're also taking corrective actions as needed, like in all equipment. You have experts on pumps, you have experts on heat exchangers, you have experts on every part of the system, right? We have the nuclear power plants, they have thousands of components and they divide it in categories and then make sure that each system is good, right? So that's gonna be something very, very important to note from the nuclear industry, that we are always fixing and improving things. So we're gonna have more on water hammer as well, but now let's jump into cavitation, right? Because if we jump into cavitation, we're gonna be able to talk about net positive suction head, which to me was like, I don't think I grasped, it's like exactly the net positive suction head part until later. It took me like a while to try to understand it, so I hope I can do a really good job explaining this. But first, what is cavitation? So Cavitation is a phenomenon that occurs in a fluid system such as pumps. So we're gonna have this can happen in pumps, this can happen like in the impellers of a ship, or it can happen like in different places. But this happens when we have areas of low pressure, right, that are created due to this rapid formation and collapse of vapor or gas bubbles in the fluid. So these bubbles form when the pressure in the fluid drops below its vapor pressure, causing the fluid to vaporize. So as the pressure increases again, the bubbles collapse and produce shock waves, right? So we're gonna have this bubble. We had a bubble somewhere. Outside we have this high pressure liquid. Then we have an implosion, vapor bubble collapse. Then when this bubble collapses, if we are close to a surface or something like that, we're gonna erode the surface, right? Because we are gonna create this supersonic like microjet here that is gonna affect or is gonna cavitate the surface. So, cavitation, this leading cause of many problems in fluid system, and it can reduce the efficiency. It can increase vibration, noise, and damage the equipment. So it can also cause erosion in a pump impeller, for instance, which can reduce the life of the pump and increase maintenance costs. So cavitation is often caused by a combination of factors, including high fluid velocity, low pressure, the presence of impurities in the fluid. So it is more likely to occur in pumps that have low net positive suction head values. So let me take a look at this. So let's take a look at this graph, right? So this is the pressure. This is the area of the pump. So this is the suction here. And I think this, I don't understand, but I can see this one in 3D for me is better. So then we have the eye of the impeller right here. So that's the eye of the impeller. And that's going to be a discharge. So the area of low pressure is going to be this, right? This is the area of low pressure in my pump. So in here, so the pressure that I have on my suction is going to be different than the pressure that I'm going to have on the eye, and way different than the pressure that I'm going to have on my discharge. That's something very important to note because it's going to help us, pick the right pump for our system. So, and that's what is going to help us to prevent cavitation, right? Because if we select the pump that is appropriate for the application and that has the sufficient like net positive head value, it's gonna help us prevent cavitation, and it's gonna ensure that the fluid, it's gonna go over with no issues for our pump. But what is net positive suction head? So we have different things happening here because we talk about net positive suction head, but we also have net positive suction head available, and we have net positive suction head required. So all of this is so confusing. So first, net positive suction head, we have liquid energy above the vapor pressure at pump inlet, right? So that's gonna be our net positive suction head. So the net positive suction head in this graph, maybe we can see it more clearly in here, is gonna be this. That's what's net positive suction head. That's our net positive suction head right there. Okay. So, but then what's the net positive suction head available? Okay, that's gonna be a little bit more complex, right? So just remember in here in this graph, this is gonna be our pressure profile. Here, if we just wanna go over this graph, from here to here is gonna be our total developed head. That we're gonna need that in the future, which means it's basically our net gain, right? In terms like you want to talk about finance, it's gonna be our or net gain. So, but then we're gonna have, so this line is the vapor pressure line, and that relates to the fluid temperature. So this line, yeah, that's what it relates to our fluid temperature. But if we have the net positive suction head, so where in here is the net positive suction head available? So what is it? So the net positive suction head available is gonna measure the absolute pressure that is available at the suction side of the pump, right? So what's available in here? So what's available in here, it has to be what it's available. It's gonna be before we start like cavitating, for example. So this part is gonna be my net positive suction head available. It's available because it's my range of operation before I start cavitating, basically, right? So this is going to take into account the pressure drop that is caused by, either fluid friction, fittings, valves, and other obstructions in the suction piping system. So it takes into account all of that as well. It takes into account the elevation difference between the pump and the fluid level in the suction tank. So it's going to take account different things. So let's go over those things. So the first one, taking account the height. Let's take a look at this part. So we're gonna have a water tank here. Imagine, so we have this tank in here. We have my bulb and my pump in here. And this is the amount of water that I have in the water tank or fluid tank. So in here, we are also considering that, we have atmospheric pressure acting on it. We have the height acting on it. We're gonna have the fluid, which is, the kinetic energy from this part acting on this. So the pressure of this is gonna be the density, the gravity, and the height, right? So we're gonna have the density, so we're gonna have the gravity, height, and density, right? In this part. So the way that we calculate the height is by this formula. Height is equal to pressure over density times gravity. And that's going to be in meters. We get that information in meters. And when we go to pumps, we're going to be able to see how everything works in order to calculate, this total developed head or other calculations that they may ask. Another important thing, it's the, we know the atomic pressure acts on the free surface of the water or another fluid, right? But, so, we also have this pressure that we can calculate its height, for instance. So, and this is going to be the formula of that only, of this atmospheric pressure in here, which is very, very similar to the other one. So now we're going to have this flow as well. But okay, before I jump into that, so we have I'll just jump into it. So we have the flow here, right? So remember that I say that flow is going to be the kinetic energy. So in order to calculate it, our head, so we use the height of the velocity is going to be equal to the like the speed square over 2 times gravity, because we only have this thing flowing in the pump, right? So what net positive suction head available is going to be, is gonna be the velocity head. Where is it? The velocity head, the pressure head, and the atmospheric pressure, right? And all of that has to be greater than the vapor pressure head. So this is going to be the vapor pressure head. So the net positive suction head includes what we talk about, the velocity head, the pressure head, and the atmospheric pressure, plus the vapor pressure head. So that's net positive suction head. Net positive suction head available is all of that minus the vapor pressure, right? So in this case, what we have that the net positive suction head available is always going to be positive, right? And well, now we have, so we see another concept now, right? Okay, and this is like another formula, like the net positive suction head available is the pressure at the eye minus the pressure saturation, which is this part, pressure in the eye of the impeller. So this is affecting the pressure at the eye on the impeller, right? But they're gonna give us that information for the exam. We don't have to calculate all of that. Was just a way to explain what's different between net positive suction head available, net positive suction head, but what is net positive suction head required? So the net positive suction head required is just given by the manufacturer, so they perform different tests on the pumps, so and they determine the net positive suction head required. And it's basically a measure of the minimum absolute pressure required at the suction side of the pump to prevent cavitation. So it's like basically telling us, oh, net positive suction head required is this, right? It's just this part. Right here, that's the minimum that you need to avoid cavitation. So in order for us to determine if a pump is suitable for a given application, net positive suction head available, let me write this down, net positive suction head available must be, guess what, greater than the net positive suction head requires. So if the net positive suction head available is less, the opposite than the net positive suction head required, the pump is going to experience cavitation, right? And what's going to happen? That's going to result in a reduced performance, vibration, noise, and potential damage of the pump. So now we understand, what's happening with those three things, which I couldn't understand for years, basically. For a year, I was like, yeah, net positive suction head available has to be greater than net positive suction head required. That's all I know. But anyway, another thing to remember is that motor amps is proportional to the work of the pump. That's all that you need to know for now. When we go to motors, that section, we're gonna go over this in more detail. For now, that's all we need to know. So now, we are gonna change gears to another subject, this other knowledge, K1.12. So in this subject, we're gonna talk about density compensated systems and not density compensated systems. So in a system that is not density compensated, only the volumetric flow rate is measured. Density compensated, it measures the steam mass flow rate, also uses pressure, to calculate that. So a not density compensated refers to a fluid flow measurement that does not take into account changes in fluid density, basically, right? In other words, the measurement is not corrected for the effect of changes in temperature or pressure on the fluid density. So there are flow meters that are not density compensated and can be affected by changes in fluid density, which can result in inaccurate readings. For example, if we have the temperature of the fluid and if we have, this temperature of fluid is going to increase, right? So we have fluid temperature that is going to increase. The density of the fluid, what's going to happen to density? Is going to decrease, right? So this can cause the flow meter to measure a higher flow rate. So in this case, it's going to measure flow rate measure is going to be higher than what is actually occurring. And similarly, if the pressure of the fluid is the opposite, decreases, the density increases, then this decreases, right? So to compensate for these changes in fluid density, the flow measurement can be corrected using, density compensation, right? And to use this type of technique, it involves measuring the temperature and pressure of the fluid and using this information to actually calculate the density, right? So we can use this information to measure, pressure, to measure, this differential pressure, density. So the density information, can be used later to correct the flow measurement, and provide a more accurate reading, for instance. So that's basically what we're gonna look at these examples. I think it's better if we go over the examples in itself so we can understand what's going on. So now we have volumetric flow rate. For volumetric flow rate, we just need to remember that what comes in comes out, right? We need to remember this formula. Mass flow rate is equal to density times volumetric flow rate, but density, we can use also this. So density is 1 over a specific volume. So if we use that, we can get this formula. So I delete this by mistake. So then we can use this new formula, right? We can substitute and use this formula, and we can also use this other formula. So if we start like doing substitution, we can get to these two formulas, right? That's the only thing that we need to know for that, basically. So now, here we're gonna go over in this other section and look at a venturi. So in a venturi, we have basically, we have a constriction. We have water flowing through this venturi, but we have this constriction, the diameter decreases. So what happens in here? This is an area of high pressure. These two areas of high pressure, low speed, but in here we have this area of high pressure, and it can pressure, like the velocity can reach like supersonic velocities in there, right? So it's just a matter of just remembering that and knowing, remembering, the mass flow rate formula. That's something that is gonna come again. And another type of problems that we're gonna have there, it's gonna be a pipe diameter difference in pipe of combined diameter. So in this case, this is trying to get us through here, he's trying to get us to understanding how we can solve problems using like pipes with combined diameter, because let's say that we have a pipe and it splits in two, right? I think that's called a pipe T. But we can have a pipe that, I don't know, we can have more. Like, can we? Maybe. So we have this pipe T, right? And we usually have this type of piping system to divert fluid flow in different directions. That's why we use it. So when fluid flows through a pipe T, it's gonna encounter a branch point where, this branch point where the flow is gonna split into two different paths, and these two different paths can have different diameters, right? So what can we do to calculate, the volumetric flow rate in each, which, if they have different diameters? So this is kind of like the formula. Well, no, this is not kind of. This is the formula that we use. We are just substituting here, and I'm just not gonna go over the substitution part here. But remember this. And this is how we get to calculate the volumetric flow rate for one, volumetric flow rate for the other one. So it tends to end up being like very simple. Once we calculate the volumetric flow rate from one, we can just calculate the volumetric flow rate from the other one very easily, right? So that's how we calculate this pipe T. Now we go back again to volumetric flow rates. So volumetric flow rate is proportional to the square root of the differential pressure. So we know that. Then we go over something slightly different, and we start looking at head loss, right? So head loss is basically a reduction in pressure or energy of a fluid as it flows through a pipeline or other hydraulic system, and this occurs due to different factors. And these factors include, frictional resistance between the fluid and the inner surface of the pipeline. It can be due to turbulence, changes in direction or elevation, and obstruction of the flow path. So frictional resistance is kind of like it's gonna be kind of like the main cause, right? It's gonna be the cause that we're gonna use the most. So this frictional resistance is going to result in a loss of energy, which is reflected in a reduction in the fluid's pressure or head, right? And this magnitude of this head loss that is due to friction is going to depend on the fluid velocity, the roughness of the pipeline surface, the length and diameter of the pipeline. We already mentioned turbulence, change in direction, obstruction of the path can also cause head loss, right? And that also can result in an increased friction and turbulence, as well as a reduction in the fluid's pressure in head. So it's important, like, to know, how we are affecting that. But to calculate head loss, we have Darcy's equation, and this is the equation that we are gonna use, right? So this equation uses this frictional piping coefficient, the pipe length, the velocity of the fluid, pipe diameter, and the gravitational constant. So for instance, if we increase the head loss in a cooling water system, we either decrease the diameter or we increase the length. Which one we change. We decrease the head loss in a cooling water system. We either open a valve, we increase the diameter, we increase the velocity, we decrease the length of the pipe, right? So that's kind of like the things that we're just basically playing with the length, with the velocity, and with the diameter in here. Length, velocity, and diameter. Everything else kind of like stays the same. We don't use it. So when we have reactor coolant pump trips, remember we have a reduction in the flow, so we're reducing the velocity. So low flow means less head loss. And a slightly greater flow is also like going to affect this here as well, but we will go over when we take a look at the example. Also, we go over flow control valves. So basically, here is telling us about what happens if we throttle the valve. If we throttle the valve more, open or close, we increase the flow. We decrease the flow, but we increase the head. So we will go over that as well. Now we're gonna go over. So we're gonna have like the final examples on the section. They're gonna talk about pumps, right? If we have centrifugal pumps or positive displacement pumps in parallel series, and what happens if we mix and match, right? So first, let's start with positive centrifugal pumps. So centrifugal pumps we're going to be able to operate them, and we're going to see examples if we operate them in parallel or in series. Because when we do that, we are trying to achieve a specific flow and pressure requirements for the piping system. That's why we start like combining things. That's the only, that's gonna be like the reason why we do that. So when we have pumps in parallel, which I don't have it in here, but when we have these pumps in parallel, what we're trying to do is so we are connecting the suction and discharge of each pump are connected to a common header. So this means that the flow rate in each pump is the same. So that's going to be important. So the flow is going to be the same in each pump, right? Flow on pump. Let's say we have 2. It's going to be same, okay? So now, as a result, the total flow rate of the system is the sum of the flow rates at each pump, but the pressure remains the same. So that's going to be important, right? So when we have 2 pumps in parallel, you have flow 1 and flow 2 equals flow total. But pressure is the same overall, right? So that's good. But when we have 2 pumps in series, so when we have 2 pumps CP in series, we're talking about centrifugal pumps. So they are installed so that the discharge of one pump is connected to the suction of another pump, right? So, okay, let me just draw this one. So I didn't, it's always good to draw. This is parallel. This is series. Okay, so now when we have them connected in series, so they are installed, as we can see, so that the discharge of one is connected to the suction of the other. So this means that the flow rate of each pump is the same. So we have the flow is same overall, right? But as a result, the total pressure of the system is the sum of the pressures at each pump, right? So then the pressure is pressure 1 plus pressure 2 equal pressure final. Right. Oops. Okay. So now we have them there, right? We have 2 pumps in parallel and 2 pumps in series. So for parallel, we have the same pressure overall. And for in series, we have the same flow overall, same flow. So that's gonna be, the difference. So that's what we're trying to play. We are trying to play if we care about the flow, if we need to increase the flow on a system but we need to keep the same pressure. So we use pumps in parallel, but if we want to increase the pressure by keeping the same overall flow, then we use pumps in series, right? So we can do things like that in order to combine operation and get this requirements of high pressure but relatively low flow rate, or vice versa. So we can play with those things. Now we go to positive displacement pumps, right? So positive displacement pumps, they work by having this. So they have this pump head and they have a certain flow. So they're gonna have a certain, like, a fixed flow rate, and you can change the pump head for the this PDP. So these pumps can also be connected in parallel to achieve a higher flow rate and maintain a relatively constant pressure. So let's take a look at this. So when we have them in parallel, this is like that. Okay, so when we have them in parallel, what's gonna happen? So when we have them in parallel, this means that each pump is receiving the same pressure, right? So pressure 1, pressure 2. They are receiving the same pressure because they come from a common header. When we get stuff coming from a common header, the pressure is gonna be the same, right? So as a result, the total flow rate in the system. So let me just go back. So since this pumps, right, is receiving the same pressure, the flow rate, maybe another color, the flow rate is gonna be divided here. So we are dividing the flow rate, right, in different sections among this pump. So as a result, the total flow rate of the system is gonna be the sum of the flow rates of each pump, and the pressure is gonna be relatively constant, right? So in this case, we have that the pressure is relatively constant, but the flow is flow 1 plus flow 2 equal to flow total, right? And why we will want to have these PDPs in parallel, right? So this is going to be useful when the system requires a high flow rate, but the pumps cannot handle the entire flow rate on their own. So in this configuration, multiple pumps can be used to achieve the required flow rate, right? So, and that's just the way that I understood. I have two, so I'm just adding on to the flow rate because I'm just stacking them up. I'm adding them up in here, right? That's the way that I understood, or that I was able to graph it for my own understanding. So, however, it is very important to note that in parallel operation, the pumps must be carefully sized and selected to ensure that they are operating within their design parameters. So if the pumps are like too small or too large, they might not operate efficiently, or you can have issues with pump cavitation or other problems. So this one's like, that's why it's very important, like for any pump, like have a proper sizing, selection, and also installation, specifically on the PDPs in parallel. Like it can help you a lot to make sure that you get the maximum efficiency of this pump in your system if you pick everything properly, right? So we're going to take a look at all of this in the examples, but this is basically it, what we are seeing on this section. This is it. This is all you need to know in order to, solve all the questions from the GFES on this section, fluid statics and dynamics.